Hi everyone, Nick Russo here, and welcome back to the BGP multi-homing series. Let's simplify our core design using multi-protocol label switching, or MPLS. This is an enormous topic, and I'm assuming you're familiar with how it works at a basic level. The goal is to create a BGP-free core, which means provider core routers like R3 should no longer run BGP. Traffic can be tunneled between PEs using MPLS, allowing core routers to rely on MPLS labels for transport rather than destination IP addresses. Since R3 isn't running BGP, it doesn't know the IP routes anymore. Our focus for the next few videos will be on the PEs rather than the core routers. Let's briefly discuss how global table IPv4 and IPv6 packets transit the network. Let's assume R4 is the egress PE for traffic flowing from R1 to R6, and that Label Distribution Protocol, or LDP, is enabled on all IS-to-IS links. For IPv4 BGP, there's nothing special to configure. If the core is MPLS enabled, R2 will perform a fib lookup on R6's IPv4 loopback on ingress and find an iBGP route via R4. R2 will then push R3's LDP label for R4's loopback, the BGP next hop. R3 will receive that label, pop it, then forward the raw IP packet to R4. R4 has an eBGP route for R6's IPv4 loopback and forwards the traffic normally. IPv6 transport requires a BGP label exchange between PEs, which is sometimes called 6PE. When R2 receives an IPv6 packet towards R6, it will perform a fib lookup and push two labels. The bottom label is allocated by BGP and is mapped to the final IPv6 destination of R6, allowing the egress PE to perform a label fib or LFib lookup. The top label is the LDP label describing the transport to R4, and it will be the same label used by the IPv4 traffic. R3 pops the LDP label, revealing the BGP label to R4. R4 performs an LFib lookup, sees that the label is mapped to R6's IPv6 loopback, removes the label, and forwards the traffic to R6. Before we jump into the demo, you should know about my Cisco Advanced Routing courses at Pluralsight. Rather than teach various topics in isolation, I developed unique, large-scale topologies to illustrate how the technologies interact. If you need to brush up on your routing protocols, tunneling techniques, or management services, click the link in the video description to get started. Now, on to the demo. The easiest way to configure LDP is to do so globally under the Router IS-to-IS stanza. This enables LDP on all IS-to-IS links, and I've configured it on the PE and P routers. This isn't an MPLS deep dive, but we'll quickly review the LDP neighbors from R3's perspective. R3 has an LDP neighborship with R2, R4, and R5 as identified by their IPv4 loopbacks. These are the LDP router IDs and are used for the TCP-based exchange of label mappings between peers. Next, let's confirm that R3 is no longer running BGP by checking the protocol summary. R3 is only running IS-to-IS and not BGP, which is correct. Let's head to R7, the route reflector, to see what's changed. As mentioned in the slides, IPv4 and IPv6 have different designs, which means we need different BGP policies. IPv4 only needs route reflection, but IPv6 needs route reflection and label exchange. This negotiates the IPv6 labeled unicast address family, allowing BGP to allocate and advertise labels for every IPv6 prefix. This is required for 6PE, which allows global IPv6 transport over an IPv4 MPLS core. Under the address family, each peer inherits from the proper template defined above. Notice the IPv6 peers are IPv4 addresses. We don't form iBGP sessions between IPv6 loopbacks anymore. That's because Cisco IOS does not support LDPv6, so we cannot bind transport labels to those IPv6 loopbacks. This further reduces the number of BGP sessions since both address families can be negotiated in a single IPv4-based TCP connection. Let's check both address families to ensure all peers are up and prefixes are received. I'll type the commands for IPv4 and IPv6 together to save time. We see all 3 sessions are up for both address families with 1 prefix received from each peer. Let's head to R2, the ingress PE. There's nothing noteworthy about R2's BGP configuration. Just like on R7, we have separate IPv4 and IPv6 policy templates, both of which use Nexthop self, but with IPv6 enabling the MPLS label exchange. R2 activates these sessions towards R7, inheriting from the correct policies. Notice that R2 continues to peer with R1 using its IPv6 unique local address. That hasn't changed. As I said earlier, this short video isn't going to teach you every step of the MPLS forwarding process. We'll limit our verification to show commands on R2. Let's check the IPv4 BGP table for R6's loopback, which R2 learned from the route reflector. There's only one route because R7 is sending its best path, but we'll fix that later. The egress PE is R4, so let's check the fib for 10.0.0.4/32 to see which label was assigned. R3 advertised label 3001 to R2 to describe the path to 10.0.0.4/32. Said another way, when R3 receives label 3001 inbound, it will forward traffic towards R4. Therefore, IPv4 packets will only have 1 label in the stack. Next, let's check the route to R6's IPv6 loopback from the perspective of BGP. This time, BGP carries a label of 4008 with the route. R2 will impose this label first, which was allocated by R4 and is mapped to R6's IPv6 prefix. The next hop looks strange, but this is a way of displaying an IPv4 next hop as an IPv6 address. We learned earlier that R3's LDP label for 10.0.0.4/32 was 3001, so the label stack on this traffic would be 3001, 4008. Again, the purpose of MPLS in this design is not to create VPNs or enable multi-tenancy, but rather to tunnel global traffic across a BGP-free core.